Okay, sounds good.
It's a seminar. I like to have a conversation.
Great. Yeah. Well, we don't interrupt that much as we should, but we'll try.
That's all good.
Okay. Well, let me just hold on. So, well, welcome everyone to a new session of our category seminar here at UNAM. It's my pleasure to introduce today's speaker, Toby St. Clair Smithe from Oxford and the Topos Institute, who will be speaking to us about continuous time open Markov processes and the symmetric NATO category. The title of his talk is The Changing Shapes of Cybercats. As always, if at any point anyone wishes to ask a question or make a comment, please go ahead and unmute yourself and ask a question or make a comment. You can also ask questions in the chat. In that case, I can interrupt Toby for you and ask a question. We'll also be having a questions round at the end of the talk. So yeah, thank you very much, Toby. Please take it away.
Okay, great. Okay, thanks. Thanks for inviting me and thanks for coming to the talk. I'm going to be talking about some ideas in what is starting to be called categorical cybernetics, so the application of category theoretic ideas and methods to the study of cybernetic systems, which I think of as those that interact with some environment and adapt themselves to it, or maybe adapt the environment to themselves. And the overarching question that I'm really interested in is effectively what makes systems tick. And in particular, I'm interested in bringing these kinds of categorical and formal methods to systems that are studied in the life sciences. So my background is in computational neuroscience, and I was very disheartened at the state of kind of thinking and modeling in computational neuroscience and cognitive science more broadly. And so I got effectively very distracted during my PhD and started using these categorical tools to effectively try and think about what systems like the brain are doing. Okay, and in particular, I'm going to talk about a set of ideas called active inference. I'm not going to go too much into this particular set of ideas, but this is kind of the kind of motivating structure behind my work at the moment. And active inference really means, or really studies systems that do statistical inference both to perceive and to act, and hence this kind of word active there. And effectively, many models in the life sciences and cognitive science in particular have a form that's like this kind of triple. So there are these three parts. And I like to think of this as some kind of like functorial semantics thing that's going on here. And so the first part is a choice of what I've started calling a statistical game. And so this statistical game is not going to be something I talk very much about in this talk, but it effectively captures the model embodied by the system of the world that's out there in the form of this thing that you might have seen me talk about before, a Bayesian lens. So this is a pair of a sort of a morphism that goes forward, so it sort of points out of the system and makes predictions about the world, with a morphism that goes backwards and allows the system to update its beliefs. And that's the thing that I call a Bayesian lens. And then there's this thing called a fitness function or a loss function, and that says in each context how good the system is, in each environment how good the system is at making inferences, at making predictions, or at surviving fundamentally. And then in these models, there not only do you have this kind of statistical thing, you also have a way of turning it into a sort of dynamical system. And you can then assign to each part of this statistical game a dynamical system that does this kind of inference. And then typically people go away and use the application of this functor that assigns dynamical systems to the games to give themselves simulated behaviors of these systems. And they compare these behaviors with stuff that is going on in the systems that they're interested in. So, activity in the brain or behaviors of biological systems or something like that. And the thing that motivated me here is a class of models in neuroscience called predictive coding. And there's a nice story to be told here, because if you look into some bits of the brain, particularly things like visual cortex, there's something that seems to have this kind of bidirectional predictive structure. The neural circuits have this kind of forwards and backwards thing going on, where some part of the neural circuit is kind of taking information from the world, say from the retina, and forming representations of beliefs about what that information means. And then some other part is going in the opposite direction and making predictions about what those incoming signals might be. And if you look at the neural circuitry, it does have this nice kind of recurrent structure. And the nice thing about the kind of categorical approach to this kind of modeling is that the mathematical structure, this Bayesian lens thing, has this bidirectionality. And the models that appear in the literature have a particular form, and that particular form is really dictated by the compositional structure of Bayesian inference and this assignment of dynamical systems to these inference problems. Okay, so that's kind of the background motivation for the thing that I'm going to talk about today, but really I'm going to talk about the kind of dynamical part, which is like this part 2 in the functorial semantics that I mentioned earlier. And I want to also situate this in the context of categorical cybernetics more broadly. And so before I get to the dynamics, I want to talk about some ideas in categorical cybernetics that are beginning to emerge and the kind of shapes of these systems, and how the shapes of these systems that I've been studying are a bit different from the shapes that other people have been studying in topics like categorical or compositional approaches to game theory that you might have heard called like open games. And then I started to feel that the reason for the difference, the kind of semantical reason for the difference, is that there are two kind of ways of treating time in these systems. And of course, it's time that really gives us this notion of dynamics. And so with that in mind, I'm going to talk about dynamics. And eventually, I want to be able to say what makes something able to do Bayesian inference in time. And in order to be able to formulate that question, we're going to need a symmetric monoidal category of stochastic processes. And really, I'm going to describe a class of symmetric monoidal categories of things like that I call generalized coalgebras, because it's not really specific to stochastic processes. You might consider things that you might want to call non-deterministic processes, and these things will generalize approaches to dynamics in coalgebra, because these coalgebras you could think of as kind of like discrete time versions of these systems. And then at the end, I'll talk about where I'm going with all this and some open questions. And then, okay, so without further ado, I'm going to say this stuff about categorical cybernetics, and in particular, the difference between these kinds of forwards-backwards processes that I have and these kinds of forwards-backwards processes that other people are describing. And it's interesting that in categorical cybernetics, there's this kind of bidirectional interaction with some kind of environment that seems to be at the heart of what's going on. And I have a bidirectional interaction that is of this kind of shape, in the sense that systems have some kind of prior belief about what's out there in the world, and they have some kind of forwards channel that they use to make a prediction about the incoming signals, say the visual information that they receive. And then they actually do receive visual signals. They make these observations, and then they have this other channel, which does this thing called Bayesian inversion, which allows them to get these new beliefs. And so notice that this goes something like from inside of the system on the left here to the kind of outside of the system on the right. But interestingly, this is a bit different from what happens in other bits of categorical cybernetics. And so there they have a similar kind of bidirectional structure. And so here I've described the shape of something that is called an open game. But the kind of where the agent or where the system comes in has a kind of different shape, has a different boundary. And so in open games, they say, okay, well, you have some forwards channel which takes in observations from the environment and returns actions. And then there's this kind of backwards channel which does something a bit strange and teleological, which says, given some like utility I got, having taken some action in the environment, I have a way of sort of passing this stuff called co-utility back in time, effectively back to systems which generated my observations. And so here, the agent is this thing that seems to come in down the top. And I've got these kind of vertical wires that represent effectively parameterization. So in the predictive case, it's like something that says, how do I make predictions? That's this parameter here. And in this kind of game theoretic case, the parameter says, how do I take action given observations? What particular choice of action policy do I have? Now, the different shapes here, this different semantical feeling is, for me, it's partly about where the boundary of the system lies. And so in this picture that I drew for my systems, the boundary lies, as I mentioned, at the kind of codomain side of the diagram. And I think of one of these morphisms, one of these bidirectional pairs, one of these lenses, is like one stage in an agent's predictive hierarchy. So you could think of something like increasingly higher level descriptions of objects out there in the world. So you've got at the very basic level, you've got this visual information coming into the retina. You might have kind of low level shape information coming in here. And you might have at a higher level representations of what objects there are out in the world. And at each stage, you're kind of becoming more fine-grained, and going in the other direction, you're becoming more abstract. So you're going sort of further away from the world into the agent. But in this kind of game theoretic picture, the agent's boundary is really at the top of the diagram. So it's kind of like orthogonal somehow. And this one morphism here represents a single agent-environment interaction. Or if we think of these things as extended in time, then this is more like one time step, and we sort of repeat this diagram in time. And here, really, time occurs effectively kind of in the wire here. It's a bit different. You have time inside the wires versus kind of extended along the wires. And effectively, I think this is what gives rise to this difference in shape. That in my systems, I have these kind of bidirectional morphisms rather, which go into the system like this, or like out of the system. But each single morphism represents one system. And then I have some other data which tells me how the systems are wired together. And so I might have one brain here and it talks to another brain over here, and there's some kind of wiring, which is effectively the structure of the environment that says how this information is passed around. And effectively what I do is I sort of fill in this box with this system up here. Whereas in this kind of open game story, the picture is more like each morphism is a system, and then the wiring in the category itself tells me how information is passed. And this kind of blends these two levels. Whereas here I've got this separation between the stuff that's inside the brain and the brains and their interactions here. I don't really have that picture in this. I don't really have that distinction in this kind of picture. And so, and really, there's no good way of talking about time here except for repeating these morphisms. Whereas here, I can sort of fill in these boxes with some kind of dynamical system, and then effectively that's what I'm going to come to next. And so I think of this as like two different ways that these kind of categorical cybernetic approaches think about time. But I'm going to have something a bit more like the second picture in order to talk about Bayesian inference. Bayes' rule is represented in this kind of, by some kind of string diagram. We'll see the string diagram later maybe, but the actual diagram doesn't really matter. But in order to draw these diagrams, I'm going to need a symmetric monodal category. And in fact, I'm going to need something a bit more than a symmetric monodal category. I'm going to need what's called a copy-delete category, which is a kind of symmetric monodal category where I have sort of comonoid structures for each object. And this is going to be somewhere where I can talk about effectively filling in these wires with dynamical processes. And so, although, so that's kind of this kind of Bayesian inference side. For various reasons, I also need a symmetric monodal category of these dynamical systems to do the thing that I call dynamical semantics, which is this functorial semantics where I assign to each morphism, to each one of these bidirectional systems, a dynamical system. And so to make this functorial, I'm going to need a symmetric monodal category which has the same kind of objects, or like same sort of objects as the category of statistical games. And so these are like pairs of spaces. And so what I'm going to need the morphisms to be are these kind of bidirectional dynamical systems. And so the bidirectional part is quite easy once you have the SMC of dynamical systems. And so I'm going to concentrate on this. And then, as I mentioned, if I have this, then I can describe this kind of Bayesian inference and time picture. And so I'm going to be able to think about predictions of the world which can change in time. And this is this kind of time, this temporal evolution happening inside these wires. And both of these stories should be able to conform to these kinds of shapes that I drew earlier. Okay, but to be able to talk about these things, we need to know what I mean by dynamical system. And so I'm going to tell you effectively what I think of as the canonical story of talking about dynamical systems using category theory. And effectively, a dynamical system is going to just be an action of some monoid, which we think of as representing time or time intervals. So an action of this monoid on some space, and we need to say fix a category of spaces. And so if we've got such a category that's nice enough, I mean, it could just be set. It might be a category of topological spaces or measurable spaces or some kind of measurable spaces. It just needs to have, I mean, ideally it'll be Cartesian closed, but I don't think it is going really to matter. So given some monoid in this category, ideally, but not necessarily, what I call a closed dynamical system is going to be a functor from the delooping of this monoid into this category of spaces. And so what does this mean? Well, okay, so this delooping category has a single object, and for each point in or time interval, so little t or little s, I get a morphism. And then the kind of monoid multiplication gives me the composition structure. So it just says that, you know, one time interval followed by another is the same as the sort of sum of those time intervals. And so a functor is going to be something that takes this unique object to a space, and it gives me some endomorphisms on that space. So for each time interval, I get what we might think of as a transition map subject to this compositionality, this functoriality rule that says if I update my system by the dynamics along this S interval, and then after having done that for this T interval, it's the same as updating my system for this composite interval T plus S. And okay, so this is a functor category, so the morphisms are just natural transformations, and that just means some map of the spaces that's kind of compatible with the dynamics. So if I map and then update according to my second system, or update according to my first system and then map, I get to the same place. So that's kind of the obvious thing, and it works nice. Okay, and now to orient ourselves a bit better in this helpful to know. The first one is quite straightforward. So if we choose time to be discrete time, so say the natural numbers, a dynamical system, and again I emphasize that these are closed dynamical systems, will be just a transition map. So this is a single map that we can iterate to give our sort of dynamical updating. So of course, if we can see this by induction. So let's see how this goes roughly. At time, with no time update, with the zero interval, this obviously means that the dynamics has to be the identity. So that's fine. But then if we update by t plus 1, that means the same as updating by t after having updated by one step. And if we think about t being 2, then this is really just saying it's one step and then another step. So really this is to say that we just update with this transition map. It's just this feature of 1 t times. So the next fact that's useful to bear in mind is that in kind of more general time, so if we have real time, we can think of these systems as being like the solutions to differential equations. So if we have this feature of t thing, we can think of this as like solutions to this dx by dt equals f of x. And it says, given some initial condition x0, it takes it to the dynamics after having integrated this equation for time t. And I get a whole family of these maps for each time t and big T. And so the third fact is that, okay, this whole framework allows us also to consider stochastic systems like Markov processes or stochastic differential equations, if we instead use functors from this do looping of this time monoid into the Kleisli category of, say, some probability monad P.
I'm sorry, Toby,
yes.
there's a question by...
Yeah, sure.
While thinking the the monoid R, do you consider the topology on that, or the smooth structure, etc.? Or you just take it discrete? Because
I'm not really going to
enrichment
consider any of the sort of. Sorry.
Sorry. I mean, do you include the enriched settings in general?
I mean, we should be able to include the enriched settings. I'm not going to make any use of that extra structure today. So really, you can just think of it quite discreetly, I think. Yeah, it would be nice to think a bit more about that in the context of the stuff I'm going to talk a bit about later. But for the development just now, it's not really relevant, I don't think. Nice question, though. Yeah. So I'll just say this last thing, which is that, okay, so in this Kleisli category of this probability monad, this says, okay, so a map in this is like, given a point, I get a distribution over some space instead of just another point of the space. And so I can consider functors into this Kleisli category, and these will be saying something like, okay, well, I get, at each time interval, I get like a stochastic update. And these stochastic updates have to cohere according to this functoriality property, this flow condition, we might say. And this is effectively what a Markov process is. And in discrete time, these things, because we have this induction property that says that they just correspond to transition maps, these really just correspond to these maps, these endo maps in this Kleisli category, which are these maps X to distributions on X. And these are the same thing effectively as coalgebras of this probability monad. So this is why I'm going to call these things generalized coalgebras. But notice, as I said before, I've been emphasizing that these are all closed systems. So there's no inputs or outputs to be considered here, just updates of some space. And really, I'm interested in systems that interact and open systems, therefore. And so I want to think about how to turn these things into open dynamical systems in such a way that I get this symmetric monoidal category that allow me to do the things I sketched earlier. And so in the literature at the moment, there are two sort of ways of thinking about this particularly. One is we can use this tool called wiring diagrams, which yields some kind of operad algebra on this operad of wiring diagrams. You can draw these kind of nice boxes, and you can have feedback and stuff like that. And, you know, it's nice. But the trouble here is that there's no way of making, if you try and open these closed systems up, and if you treat these open systems themselves as morphisms in something you might want to be a category, you find you can't make composition be unital. You don't get an identity dynamical system, effectively. And so for my purposes, that's no good, because really I want a symmetric monoidal category, not, say, a symmetric monoidal semi-category or something like that. Okay, and so the other thing that people do is they consider these things called decorated or structured cospans, which in this kind of operad formalism gives you a cospan algebra. And of course, this yields a symmetric monoidal category, but it doesn't work in the kind of general setting that I want. There are some technical conditions that need to be satisfied. You need some effectively left adjoint from category of spaces into category of systems, which I don't have in general. So you can't do this for general stochastic differential equations or other things that are known as random dynamical systems, which effectively are bundles of dynamical systems where some parts of them are measurable. And a lot of the models in the literature are framed in this more general setting, and so we can't really use this SMC of decorated or structured cospans. And so we need something else. And there is another way. I'm going to define an op-index category of, or a family, effectively, of op-index category of these generalized PP coalgebras with time t. And sometimes I'm going to write t this blackboard style, but sometimes I can't be bothered. But it's slightly silly. I've got this little p which represents a polynomial, and we'll say what that means in a minute, and a big P which represents my monad, because I think of it as like a probability monad, but you might also think of it as power set or something like that. And I'm going to say, okay, given this op-index category, I have a way of turning it into a symmetric monoidal category. And the way that this is going to work is I'm going to say, what are the functors between the fibers? And so the morphisms in this SMC aren't going to be systems themselves. They're sort of going to be ways of transforming systems. they're going to be what we might think of as systems with holes in them. And this, luckily, this SMC is going to restrict to this thing I mentioned before, this copy-delete category, as long as we restrict the object in some appropriate way. And this means that we'll be able to formulate this notion of Bayesian inference in time. Okay, but in order to be able to get there, I need to describe these things called polynomial functors, because these polynomial functors are going to represent the interfaces to our systems, the things that make the systems open rather than closed. And so we're going to use these polynomial functors to describe these shapes that I've been saying of the systems, and this like pattern of interaction, which effectively generalizes this wiring diagram story that I mentioned earlier. And I drew this picture previously in this suggestive way, because this is really going to give me this op vibration, and I'm going to have a category of systems over each polynomial box or polynomial shape. And following David Spivak, I'm going to write polynomials in this way. So I've got this y to the a plus y to the b, and there might be some coefficients in there. And effectively, I can group all this stuff together into a sum over some positions of y to the set or space in that position. So this p represents my polynomial, this p of 1. So these polynomials are going to be polynomial functors, effectively, like this. And p of 1 is what happens if I compose this polynomial with this terminal object. And this is going to give me just a set. And this set is the set of summands. So all possible, y to the a's or y to, it's all of these positions. And in each position, I have an exponent, and that's what this p of I is here. And I drew, well, I and Vivek uses this square bracket notation because this isn't really, this is like pulling back p along, this I, which is an element of this. It's not composing I with p effectively, so it's a different kind of bracket. And as I said, these are functors. They're effectively co-presheaves, and this y to the x is this kind of representable co-presheaf on x. Now, this kind of formal functor structure is not going to be particularly relevant to us, not today at least. So I'm going to eventually write these things as bundles. I'll show that in the next slide. But the semantics for this in my universe is that these summands, this set p of 1, represents the possible configurations that a system might take, its shape, or like whether it, say, its eyes are open, or where its limbs are, or something like that. And the exponents are these dependent incoming signals. So for instance, if your eye is open, you have a set of incoming signals which includes visual information. If your eye is closed, then you don't get this visual information. And so the possible incoming signals depend on the configuration of the system. Excuse me. Okay. But I'm going to work mostly with this bundle representation. And so given each one of these things in this form, I can make a bundle like this. I can collect all of this. I can make this dependent sum of all the possible coefficients. And it's, of course, a bundle over the configurations. And this is effectively obtained by the Groton deconstruction applied to the opposite of this slice functor here. So it's taking the slice over this object, which we might consider the kind of base of the bundle. Okay, and so the morphisms between these polynomials are the morphisms you get from the Groton deconstruction. They are, say, a map that goes forwards like this on sets of configurations. It says, given some configuration of this P, I get a configuration of Q. And as well, because I've got this op thing going on here, I get a morphism that goes backwards that says, given some incoming signals in the position over P, having pulled back this Q map, so this is a Q incoming signal, I get a P incoming signal. So this tells me how to sort of translate Q incoming signals into P incoming signals. And the composition of these things is not something I'm going to use very much today, but it's the obvious thing you would get from the Groton deconstruction. You just compose the forwards maps, and then you pull the second backwards map back along the forwards map of the first, and then you compose the things you get in the only way you can. Now, I'm going to use the monoidal structure of these polynomials. So notice in the diagrams I've been drawing representing wiring, there's some way of putting systems in parallel. And that corresponds to this tensor monoidal structure. There are a number of these monoidal structures, but I'm particularly going to be concerned with this one. And it's quite simple. It works by just forming the product of the sets of configurations, and over each element of this product, each pair, I form the product of the corresponding sets of incoming signals. So really, it is just putting things side by side. And on morphisms, of course, it's the same thing. I just take the product of the base maps and the product of the kind of backwards maps. Now, another thing that's good to know, and that will be quite relevant later when we come to talk about the copy-delete structure, is that there is an embedding from this category of spaces, which really we often just think of as set, into polynomials over the spaces, which takes a set or a space to the linear polynomial AY, which as a bundle is just the identity on the space A. And you can quite straightforwardly see that if you take this tensor product structure and you restrict to these linear polynomials, effectively what we're doing is eliminating these backwards maps. And so this tensor product restricts to the categorical product on the category of spaces. Now, okay. So let's think again about these open systems, these open dynamical systems in particular. And I want, for each polynomial, P, I want a category of systems over P that are open analogs of these closed systems that I introduced earlier. And I'm going to work with this functor category because, of course, I could always choose P equals the identity, and then I would just get these deterministic systems. And I want these open systems to be like the objects of this category, but open. And so what we're going to do is think a bit more about this figure opposite. Think a bit that these systems effectively inhabit the boundary determined by the polynomial. And so what do we get if we think like that? Well, we get objects that are like this, like these triples. The first part of the triple is a state space. So that's the thing that in the closed system is the points of which are kind of transitioned or updated. And then there's a way, and then I want a way of turning a state into a configuration, and that thing I'm going to call an output map. And because I have this temporal structure, I want this to be a time-indexed family of output maps. And then to make the dynamics part happen, I need some way of giving new states from old states, and that's this update map. And this, it looks a bit intimidating, but all this says is for each time t and state x, I get a way of saying, given some incoming signal that's relevant or that's kind of possible in this state x according to the output map, I get a distribution or some way of some element of this monad applied to x and some distribution over states that we could think of as kind of the next state, say. So this is saying, given some input, I get a state where the input is kind of coherent with the state, I get a distribution over states. And then I can kind of use this closure property, which I'm going to mention just now, to kind of say that this works like a dynamical system. And so what does that mean? How do I make this work like a dynamical system? Well, I need a way of turning these triples into the objects of this functor category. And I call this process closing this system. I form this closure. So for any section of the polynomial, now we can think of the sections of the polynomial. So P, the polynomial goes from this, it projects down from this dependent sum into this base type. So a section goes the other way. It says, given each configuration, I get an input. And so it's a way of saying assigning inputs to configurations. It's a way of saying what the environment gives the system, given each configuration the system takes. And so I say, I need to satisfy the condition that for any such section, I form this closure, and that this closure forms an object in this functor category. So what is this closure? It just says, well, I pull back the section along the output map in order to turn it into a map of the right form, and I pre-compose that before the update map. And this says, okay, well, now I get my state and the input according to my section, and now then I do the updating, and I get a distribution over states. And I say, okay, when I fix a section, I can then iterate this thing just as I could a dynamical system before. And then this is the thing that I call the closure, the thing that I want to be an object in its functor category. And I write it like this. Given a section I give and a system theta, I write theta for the sigma. Okay, so these things will form a category. I'll show you how in a minute. But first of all, let's orient ourselves again and think about some facts of this category. So in the case where I choose this trivial polynomial where I don't have any inputs or outputs, we could think of that as a closed system. Then, of course, I get the thing that I want. I get this functor category back. So we really do think of this functor category as a category of systems with no inputs and outputs, a category of, therefore, closed systems. And as I mentioned earlier, if I choose the monad to be the identity monad on my category of spaces, I just get deterministic systems. So that's nice. And then if I choose time being discrete, so natural numbers, one of these triples is really equivalently a coalgebra of this composite monad, this composite functor rather, P. So this is little p, the polynomial, after this probability monad. And so this coalgebra, okay, so what are these coalgebras? How do we see that this makes sense? These coalgebras are equivalently, just by the way this polynomial functor works, typed like this. So it's like a map from X into the dependent sum over configurations of this exponential from inputs in that input spaces in that configuration into distributions over the state space. So if we unpack this dependent sum by the universal property, we get a pair of an output map like this and an update map like this. And so I've got a space and an output map and an update map. And so I've got this triple that I started with. So really, this is a way of thinking of like PP coalgebras with time t. So that's nice. And I really want to know more about the theory of these things. And I haven't really had time to establish much of it myself so far. Okay, so right, it's a category where it's...
I'm sorry,
yes.
Toby. What do you get with when you have your indexing for boundary polynomial to be constant? Is that what are dynamical?
Do you mean just like A? So
yeah.
No Y at all? Yeah. I think you don't have any, so you don't have a Y. So this is like isn't this like the, oh God, okay, hold on, my remarkable things crashed. Okay, well let's try again. Maybe it'll work. It doesn't work. Hold on. So I think the answer to your question, which I can hopefully say while I figure this out, is that this is very strange. Hold on a second. Is that we get sort of trivial systems. We get just spaces and no updates because we have the bundles are like the map out of the initial object.
Yeah.
Is this going to work? Okay, it does work. Strange. Yeah, so here the bundle is just this map.
Yeah.
Because there's no Y effectively in the polynomial, and so if you work that out, what does this have to be? Then the update map, the state space is this trivial thing, and then this kind of deteriorates into like a trivial map, and so you just have. I think this category corresponds. I think probably coal of. I don't know. I would hesitate to say. I think there's a way of kind of just getting E back.
Okay.
But yeah, so you don't get anything interesting.
Okay. Thank you.
Okay. So those are the morphisms. Yeah. So the morphisms are just like the maps maps between state spaces in the same way that we had before. We say for any section of the polynomial, we get a natural transformation between the closures. And so that's, okay, so that's nice. And okay, so then what, I want this to be not just a collection of categories over polynomials, but particularly an op-index category. And so that means given a morphism of polynomials, so that's a pair on sort of a map on the configurations and a backwards map on, that says how to redirect the incoming signals. I need a way of kind of rewiring the dynamical systems, and that's quite easy. What we do is we sort of post-compose the output map with my F1, which tells me how to get new configurations of Q, and I pull back the sort of backwards map along the output map, and I get a way of saying taking inputs, Q-like inputs into P-like inputs, and so this gives me a system over Q. And we need, okay, so we needed these things to satisfy this closure condition. And the way this works is that, okay, so I said that the system has to be closed with respect to any section of P. And so I need this also to satisfy this new system to satisfy the condition that it's closed with respect to any section of Q. And so what we do is we observe that if we've got a section of Q, then we say, okay, well, what's this thing going on here? I need to make this closure an object if this functor category for any section. So what does this mean? It just effectively means that I get a section of P from my section of Q by using this map. And so because it worked for any section of P and I've got a section of P, it works for Q too. So the proof is in the paper, which I'll refer to later. But it effectively says I can just take sections of Q to sections of P. Okay, so now I've got this op-index category. I want a way of turning it into a symmetric monoidal category. And so, as I mentioned, we're going to consider these functors. And the way I think about the functors between these fibers is that if I have a functor from coalph P to coalph Q, I think of this as like a Q-shaped system with a P-shaped hole. So it's kind of like, so in this category of polynomials, we have this internal Hom with respect to tensor. And this is like, these functors are like a kind of like externalization of systems over this internal Hom. Okay, and so to make this a bit more concrete, I'll give you a kind of class of examples in a minute, and the class of examples are going to use this fact here, that this op-index category is lax monoidal with respect to this tensor. And the laxator does the obvious thing. So it says if I've got a system over P and a system over Q, I have a way of getting a system over this tensor of P and Q. And the way is I take the system over P and a system over Q, and I just take their product. And of course, that's a system over this space. And it's over this tensor. And really, of course, it has to be lax because I might have systems over the tensor which don't decompose like this. So it only goes in this one direction.
I'm sorry, Toby. This is again the Dirichlet tensor product. This is the one that you chose before.
Well, yes, yes. I don't know if it's the Dirichlet product, but it's this thing that I described earlier.
Yeah. Well, the one. Okay. Yeah. Thank you.
Okay, and so let's orient ourselves again a bit more. So if I just take these simple like polynomials like these, like monomials like this, okay, so if I've got y to the a, then the internal Hom thing is like a y. So and so how does this work? Well, I want to be able to evaluate these things. So given y to the a and p, this kind of square brackets py, I can sort of wire these a outputs into this A inputs, and then this gives me just a closed system. And okay, so we have kind of other like evaluation morphisms like this, which work by wiring. And so we take the outputs of the system and we wire them into the inputs of systems over Q, and we just get like system over Q. And we have other kinds of sort of more general wiring maps like this. So if I've got a system like over AY and a system that takes in A's and gives me B's, so a system over by to the A, I have a way of sort of wiring the A's into the inputs here, and then I get this system that gives me just like B outputs, and there's no A inputs anymore because I've provided them. So given a system with A inputs and B outputs, so that's a system over By to the A, like this, theta, we obtain a functor from coalg AY to coalg BY by saying, okay, well, I use the uniter, so I get coalg AY times 1, and then I choose the elements theta, so coalg AY times coalg BY to the A, and then I use my laxator to form their product, and so that's a system over coalg AY tensor BY to the A, and then I have this wiring morphism, which I sketched up here, and of course this is a this is an op-index category, so I can sort of use the image of this morphism in this op-indexing to sort of wire the systems up in the way that I sketched earlier. And then this gives me a system over By. And of course, this composite is a functor coalg AY to coalg BY, which justifies this previous intuition that I think of these functors as systems that are like, that here it would be a system sort of with B outputs, and it's got a hole that takes in A inputs, or effectively outputs of some other system, or those other systems' behaviors. Of course, there are sort of more general functors too, but this is a good way of thinking about these systems intuitively, these functors intuitively. And I'm going to write the name of this category of all the functors between fibers of coalg as coalg poly with this over line, because it's like the image of this op-index functor, op-index category under this whole of poly, but it's really completed to all of the functors. And of course, this is a subcategory of cat. And I'm just going to write its objects as the polynomials themselves rather than the categories with this complicated name. But here we'll stick with this complicated name for now until we get used to it. And we have this nice characterization of these functors. All of these functors are equivalent to triples like this. We have an endofunctor on the category of spaces, which I'm going to write as f dot. I get a t-indexed family of morphisms of polynomials, which effectively say at each point in time, how do I like wire the system according to this? How do I get the Q shape from the P shape using, having given this functor? And then I have this other part, which is a t-index family of natural transformations. So I think of this part as giving me like the new state space. This part is telling me how to do the wiring, and this part is somehow like distributing F like P over F. It's not quite a distributive law in the sense of coalgebra, but it's something like that, and it also does something else. It supplies the dynamics. So how does the proof of this go? Well, I'm not going to go through the whole thing right now, but it's instructive to look at it if we just consider these linear polynomials AY. Okay, so if I have a system like this, really if I have a category of systems over AY, then it's state spaces, it's triples of state spaces, output maps which are just into A, and update maps. Okay, so I don't have any inputs, so it's just T times S into PS. And functors like this are they have to, from AY to BY have to be a map on each factor of the triple. So it's a functor because I have a category of spaces here. And then by Yoneda, I get maps F dot A into B, because effectively if I let this vary over the spaces, I get these pre-sheaves. So this is a T-index family of natural transformations. This is a representable. And so I just use the Yoneda lemma to give me a T-index family of maps F dot A to B. And so in the general case, that's F dot P to Q. But here I just had F, A and B. And a similar you get a similar kind of reasoning that gives you a family of natural transformations down here. Okay, so I'm just going to work with these triples from now on, because they're easier to work with, and they're going to give you a better intuition for what's going on. And as I said, we think of the endofunctor part as returning the new state space. So like a typical choice would be like something like this. Like give me like some new factor like this, some new state space. This tells me how to do new wiring, and this supplies the new dynamics. Okay, so now what we can do is if we make some further assumptions, so in particular that this endofunctor is co-unital, So if it's like this, then the co-unit would be the thing that throws away this part and just gives me, no, sorry, that's obviously not true. Throws away the S part and just gives me this part. Then I'd say that this kind of plays well with the polynomials. I want them to kind of obey this isomorphism. And then I can write down a kind of nice recipe for how this acts on the systems. It's this complicated thing here, but effectively it does say just the intuition I gave earlier that this F1 part does, or this F part does, this little f part does the rewiring. This endofunctor gives me a new state space. And then this says, okay, I need a way of giving me new inputs. This is my sort of new update map from the old update map. And then this bit says, what's the new dynamics? This might be some other dynamic, some other update map here. And those things composed according to the same rules, of course, as the functors. Now I can lift this tensor to this category of functors between fibers. We can't just use the kind of naive thing, which is to use the categorical product on cats, because what we would have to do there is say duplicate a system, throw away each part, and then use the laxator to put them back together again. But because the functor would therefore be defined with this duplication, it's never going to be functorial, because on one side I have two duplications, on one side I have just one duplication, and so I get too many duplications on the left and not on the right. So that doesn't work, and we need another way of doing it. So what we're going to do is we're going to do something that looks a bit strange. I'm going to define, of course, the object's going to be the tensor of the objects. And then on these triples, I'm going to say, given this f dot and the g dot, I'm just going to compose them. And then given the maps of polynomials, I'm going to form their tensor. But because I've got this composite functor, I have to have this co-strength thing. And then I have this funky way of composing the natural transformations part. And unfortunately, we don't have time really to go into all the details here. But to make this thing work, I need to impose some conditions on these functors. In particular, they need to be commutative like this. And I need to have this kind of co-strength thing here in order to distribute the f to the left and the g to the right. Now, it's quite lucky that these conditions are satisfied in the common case. So the common case that I described earlier, where I have the functors acting like tensor systems and wire them up. So I take in a system and I have some other system which takes in inputs of this type, and then I wire them together to give me systems of this type. But it's still an open question to me. I don't really know what to make of these commutative, co-strong, co-unital functors. And I sort of suspect, I don't know, I haven't proved it, I haven't had time to check really, that these conditions might make them very close to just being product functors like this. It would be interesting if they're not. I haven't really figured it out yet. But so if I have these functors, at least I can make this monoidal product work. And that's nice, because it means I can write down these morphisms which have kind of updating happening in the wires effectively. Now, I seek more than just an SMC. I want a copy-delete category, so I can sort of talk about this notion of Bayesian inversion in time. And Bayesian inversion is defined by this string diagram, which I started to sketch earlier. And I want to be able to draw diagrams like this in my category. And a useful fact to have here is that there is an embedding of poly into my category of functors between fibers, my category of generalized coalgebras. And it works by taking the identity on functor part and the natural transformation part and just using the polynomial map for the family of maps of polynomials. And we think of that as just like saying, don't do anything to the system, just post-compose the wiring. Now, to make the copy-delete structure work, to be able to do this kind of like copying and deleting, we can't just use, for a similar reason that we couldn't use the sort of product structure of categories, we can't use the sort of canonical co-monoid structure on categories, which of course gives you functors, because we have the same problem of mismatched duplications. If we try and make this copying natural, you get the same problem occurring. So we can't do this kind of naive choice. And now the other naive choice is that, well, we might want to work with the whole category of functors over polynomials, but this isn't going to work because there's no way of discarding a general polynomial, because a map P into the monoidal unit Y is equivalently a section of P, and obviously there's no canonical choice of section of an arbitrary bundle. Now, of course, if we worked with co-pointed polynomials, so if we just equip them with sections like this, then that's fine, but that opens a whole other can of worms, which I don't want to get into today. The simpler thing to do is to restrict to these linear monomials, these polynomials AY, and then there is an embedding of E, as I mentioned before, into polynomials, which works like this. And there is a copy-delete structure in E, and there is this there is this embedding of polynomials into coalgebras, into generalized coalgebras. And so we can just lift the copy-delete structure through all these embeddings. But it only works because we make this restriction to generalized coalgebras over the linear polynomials, which I'm going to write as coalg E. Now, so that's nice. So we get a copy-delete structure. We can check that the resulting structure does obey the comonoid laws and it does cohere with the monoidal product. So it gives us that we have all the structure we might like. And that means we really can draw this Bayesian inference diagram. We think of this as like correlated copying. So what we might, how this works is because we're just post-composing with this copy map, say, effectively it says the system gives us outputs of this type and then we copy them. So we think of those copies as, of course, correlated according to the dynamics that's happening sort of behind them. And this allows us to formalize these pictures that we'd see in the literature where we have kind of like two kinds of coupling. So we have these informal pictures where people sort of draw nodes that are coupled in sort of horizontal and vertical ways. And these nodes like represent spaces and the lines represent couplings. And so this is like time occurring horizontally and sort of structural coupling, which is more like this, the morphisms in the kind of copy-delete category normally represent happening vertically. And the nice thing that we get from all this is that we can then define dynamical statistical games. So these are the statistical games where you have some kind of predictions like evolving in time, Bayesian inference evolving in time, just like systems in the real world do. Okay, so I don't know if this gets us very close to reconciling these two pictures. It certainly gets us a bit further to this side because we now have systems, we now just have like this symmetric monoidal category, and it's not hard to equip it with a parameterization. But it's still not, I mean, this isn't really where I feel like we should be. It's only here, I'm only here because I need to be for Bayesian inference. So I don't know if this is really the best way of thinking about reconciling these two pictures. Another way is that in the kind of open games community, they're kind of starting to work with these co-precies on this category of optics. And this category of optics is a bit like a kind of like sort of monoidal or linear version of this category of polynomials. And of course, these co-precies are really like these op-index categories. So there's something similar happening in these two stories here. I still don't know quite what it is, but at least we seem to be getting a bit closer. Now, a thing that still is on my mind, has been on my mind for a long time, is I want to understand systems within systems. So I want to say, okay, well, if I've got some box here, and this is like some brain, or like some representation of some agent. Effectively, I want to be able to put another system inside it. And that's like saying in these pictures, I want to be able to put something in here, some other kind of dimension, some other like third dimension of parameterization. So parameterizations of parameterizations. And there is a way of doing this with these dynamical systems with this, because we can sort of say, okay, well, given a polynomial, you can write it as a bundle like this thing that people call a bridge diagram. But if we take these trivial types and make them a bit more general, so if we say J and I instead, and we then say that, okay, these J and I types have to be also a bundle, and these two bundles have to be sort of coherent in some way, then we could think of this as like a box within a box. And we could put a dynamical system in this box and a dynamical system in this box. And of course, to make that nice, these two things have to cohere. And this is something that we can do and we get a double op vibration. And I think if we apply this recipe that I used to give a symmetric monoidal category, we effectively get something that's a bit like a sort of symmetric monoidal double category. And the question that's on my mind and has been on my mind for a while is that what happens if we iterate this? Of course, we have systems within systems within systems. And if we take that iteration up to infinity, I don't really know what the structure of that thing is. Is it an infinity vibration? What does that mean? And how does it relate to this thing I mentioned earlier of reparameterization? So these are my kind of open questions here. And then there's this whole other branch of open questions, which is how do these ideas relate to coalgebra, which is this approach to talking about dynamical systems in computer science? And in particular, are these structures that I've described well known? I don't think they are, but they seem to be quite nice. And how does coalgebraic logic relate to these kind of more general time systems? I think that each of these categories of coalgebras over this polynomial is a topos. I haven't fully checked, but I strongly suspect that this is correct. So I always wonder what's the connection between these two logics. And in particular, I would like a kind of neater way of defining this category that doesn't require this kind of complicated closure condition. But I don't really know what that is yet. And so finally, the other thing that I'd like to check soon is whether this category of this SMC of generalized coalgebras is traced. And so because I can draw diagrams like this in my category and have kind of dynamics occurring in these wires, I feel like if these two things are of the same type, I should be able to do this and get a box like that in a way that obeys the kind of trace rules. Of course, I feel like I should be able to plug an output of a system into itself if it has a corresponding input of that type. I don't see why this shouldn't work. I just haven't checked on what this means. So I think I'm out of time, and I think that's the end of my talk. I have this preprint notions of open dynamics or something like that. And I'm going to add the rest of this material to it kind of towards the beginning of next week. Then I'm going to make a kind of shorter document, a kind of more digestible paper about it. But yeah, so thanks for listening, and sorry for the weird bug in the middle of it, but cheers.
Thank you very much. Thank you very much, Toby. Are there any questions or comments for Toby? Yeah, please, Carlos, go ahead.
Yeah, thank you first for the talk. It's really nice subject. My question is about Petri nets. You at the beginning of the talk, you mentioned that you start with some statistical gain and then you produce a dynamical system. And
yeah,
you use these two things in order to simulate. So Petri net at the end is the purpose is to simulate a discrete dynamical system. And so really, I don't know if you can say how the Petri nets get into your procedure, and also about if you can clarify that if there's the idea of Petri was that the time is included, for example, in the stochastic Petri net, is included locally, because it was motivated by the ideas of Einstein. So the time in your procedure is follow that ideas, or there are different. That's my question.
Interesting. Well, I guess I'll maybe answer your questions in reverse order. So I should start by saying I don't know an awful lot about Petri nets except for a couple of things. One is that I think their category or their categorical description typically falls into this formalism, and that's really nice. It'll be really nice if I could do something like that with the systems that I've been looking at. But I guess they are quite. I mean, they have a kind of more restricted setting. I think they typically have. Then they typically have like finite sets of states, and they have this kind of linear dynamics, which I I feel like I have something. I mean, these things are a bit more general, and so they don't quite compose in the same way. Now, I do suspect that there should be a way of translating the kind of rate equations you get from Petri nets into this formalism, but I don't know if that would be functorial, because I don't know if the composition works the same way. Because there's this kind of co-span algebra structure happening here. But I don't know, it's not something I've checked, and I really should look into it. As for the question about time, so time is global in my systems. And I don't know how I could make it otherwise, to be honest. But it's a really nice thought, because actually I think maybe we shouldn't think of it globally. But the reason why I've done it like this is that it just sort of corresponds to what people do in modeling for the systems that I'm interested in. But yeah, nice points. Yeah.
And only one more question. Yeah.
Yeah.
Suppose you have a problem, a dynamical system, maybe continuous, discrete, and you don't know the monoid, because for me it was awesome this definition of dynamical system as a functor from the looping to topological space. No? And so how you can find the monoid of symmetry?
I don't know. So, I mean, typically people just choose, right? They say, oh, time, like it's often motivated by where people are coming from. If they're just working with like computer systems, then they'll typically use discrete time, or if it's a physical system, they'll use something else like the real numbers. But one thing that's I'm curious about, which I don't think I have right now, is the ability to talk about hybrid systems. So often people want to talk about systems where some parts have these kind of discontinuous transitions, and so that would be using this discrete time, and other parts evolve continuously. Say you're kind of, I don't know if you're modeling neurons and they have this kind of like, they have this spiking, which is very discrete, but obviously the rest of the world you might want to treat in a kind of continuous way. But here you really have to fix this time, and then that's it. You don't have much to do apart from fix it. But one thing I think you could probably do is say, I mean, we have this functor category like this, and I guess if you just let this vary, you probably get an index category, right? So you get an index category of functors of systems over different monoids of time. And then I guess you could make a construction in which, if you've got some way of like embedding discrete time into real time, you probably get an equivalent way of wiring up systems using that recipe. But it's not something I've explored yet.
Mm-hmm. Yeah, it looks like you are finding the element that represent your correct these things that are representative, that are well, you know how to say it. Yeah, for example, there are some functors, and you want classifying space that make this functor representative. So here's co-representative. Something like that. Maybe I don't make my sense.
Yeah, I don't know.
Well, thank you.
No, thank you.
Thank you very much for the question, Carlos. Are there any questions? Are there any other questions or comments? Yeah, could you say, well, I'm sorry, if no one else is asking questions, I might ask a few, if that's okay. Well, could you say a bit more of why couldn't you from the beginning define your symmetric monodal category of open dynamical systems through wiring diagrams. You sort of mentioned this, but could you maybe say a bit more about that, please?
Yeah, okay. So let's see if I can remember the details right now. So like, okay, so if we have systems like this, let's say they don't, yeah, we'll just say like S to A and like it's discrete time, so B times S to S, then what effectively we would want this to be, this is out, maybe I should say B here. So output B and input A, this, I want this to be like a morphism A, maybe we notate it with S to B. Right. And so this is a kind of, this is discrete time, it's no stochasticity, and it's over this polynomial, effectively, what should I say, dy to the A. And I want this to be a morphism. But okay, that would be a morphism like this. And so really I need another morphism. I need this identity morphism, A to A. And so what's this going to be? This is going to be S to A times S to S. Now, if you say, okay, this is going to be an identity, we need it to be able to like compose with this system in such a way that we get this system again, right? So effectively, I need to somehow compose these outputs here, and maybe we call this S prime, and then this composite system would have to end up being the same thing, but I don't really know, like what is our choice of S prime, and how does this work? And I swear, if you go away and you try and figure it out, you're not going to find an identity that makes this composition, or a composition rule that makes this, that gives you an identity system.
Okay. Okay. Yeah, I think I'm happy with that. Yeah, that would be the sort of like the first, I don't know, intuition option or whatever. Yep.
Yeah.
Okay.
And I struggled for a long time trying to work with this, make this thing work. And okay, so you can if somehow make these things into like stands.
Yeah.
But these things don't really compose in the way that I want. So you don't get the structure that I was interested in.
Well, also, I suppose when you well, I don't know, when you write everything down and so I was just curious about the choice of the tensor product on polynomials.
Okay, why?
Well, I mean, well, it seems like you do make a choice. So how many tensor products are there in polynomials? 4, 5? I don't know.
Okay, there are a few. So there's this one, there's this one, there's this composition product. Right. There are others as well. Of course, there's like plus.
Right.
Actually, that's 0. And then there's this other Dirichlet one. I don't know how you would call that. I don't know what the unit is either, but yeah. So I think there are 5 at least.
Yeah, yeah. So, well, so yeah, my question is just out of curiosity, why I mean, when you were doing this, how did you choose the out of the 5?
I chose the one that has this semantics of putting systems next to each other, because what would that mean? That would mean that if I've got a system over P and a system over Q, then I get a system with P outputs and P inputs, and a system with Q outputs and Q inputs, and really that is precisely this thing.
Yeah. Okay.
So I mean, it's only that. But I think this recipe that I gave of, if you've got these, I won't go to the slide, but if you've got these commutative co-strong co-unital where the co-strength and co-units are, or where the co-strength rather is with respect to any of these monoidal structures, you should be able to get a symmetric monoidal category there too.
Yeah. Okay. Yeah. Well, also, could you say a bit more about the co-strong condition for for functors?
So what would you like? What kind of thing?
Yeah, I don't know. We just yeah, just so what does that mean? I mean,
right. Okay. Okay.
And what does it do? I mean, that's I guess that's my question. I'm sorry if it's
right. So what? Okay. So let's see. Let's have another page again. So I said I'm going to form the tensor like this. Yeah. So if I have these two, so I have these triples which represent the functors, and they have this, say they have this wiring part. So I've got these two wiring parts, and I want effectively to put them in parallel. And I also want to kind of put these functor parts together somehow. And the only way really that I can do that, because these are functors like this, is I can compose them. And so the first thing I need is this commutativity, because of course I need, well, if you work it out, you need this f prime tensor g prime is naturally isomorphic to f tensor g after f prime tensor g prime. And you'll see that if you do this thing, you'll end up with f prime g on one side and g f prime on the other. And you need these things to be naturally isomorphic, so you have to have this commutativity. So that's the first thing you need. And the other thing you need is, because these things, these triples, act by saying they take the system and they go like effectively this, and so you get part of your system with an update map which is f dot theta o, and that would be something like f dot s to f dot a, and say my other type has the output of b, then I need a map like this. Okay, so that's fine, but of course if I'm doing this tensoring, then I need to go something like f dot g dot a times a prime to b times b prime.
Yep.
And so first of all, I need a co-strength that will go f dot g dot a times a prime to f dot a times g dot a prime, and then f dot a times g dot a prime, and then this can go b times b prime. So I need a way of like effectively distributing these things.
Right.
Like that. So that's this co-strength. And okay, so there are also some axioms that the co-strengths have to satisfy, but they're trivial things. Well, they're not trivial, but they're the obvious things, like they have to behave well with the tensor products and the units and blah, blah, blah.
Yep. Okay, yeah, that's, thank you. I think, I think that's all. I'm sorry, my questions were not very productive to you, probably.
No, it's always good to explain stuff. So
well, so I guess I do have a final question. So
great.
What was so frustrating about the non-categorical methods in neuroscience modeling? Or I mean, yeah, that got you so annoyed. And
so there are like two principal things. Okay. The first thing is kind of people live in their own universe and they come up with some ideas, and some other people in some other universe come up with some other ideas, and it turns out those ideas are fundamentally structurally very similar, but nobody notices because they're written in different languages.
Yeah.
And they're not written clearly. And so that's the other thing, is that people don't really have the mathematical tools to describe systems of the complexity that they're dealing with. And in particular, these are complex systems that are composed of lots of lots of components, and they don't really know about how to sort of kind of disentangle this complexity. And in particular, in this kind of active inference world, there are a lot of papers where people draw like models like this, and they have some compositional structure, and then they give some kind of dx1 by dt thing, and you get, for each of these parts, you get a differential equation, and they're always of the same rule, or the same form, but every time they have to rederive the differential equations because they don't notice the compositional structure. Mm-hmm. And because the compositional structures end up being quite complicated, you get papers where there are loads and loads of indices and nobody understands them. And it would just be fundamentally easier if people kind of, one, understood what each other was saying because they were working in a formal language where they could say, oh, this is the structure that I'm working with, and two, didn't waste all their time rederiving things that are fundamentally like, if you know how to do this for one part, then that's all you need.
You don't have to spend your time reading indices and figuring
out
what they mean. Okay, that's.
And I guess the third thing is that there's a load of beautiful mathematics that comes with all this stuff, like to do with algebraic topology. It's just really not available if you don't use that language.
Okay. That sounds very frustrating, to be honest, and very apt for applied category theory for I don't know.
But, I hope so.
Yeah. Well, it's a really beautiful talk, Toby. Again, I'm sorry I didn't have more interesting things to say, but it was really nice, and I myself really enjoyed it.
Thank you very much for inviting me.
Are there any final questions for Toby from anyone?
Maybe I can ask about, I hesitate to ask, but before, do you, in your dynamical system, are you interested in reversibility?
I am, but I don't know what I can say about it.
For example, if you take the natural numbers, you don't have, the
backwards time.
Yeah, you don't have backwards time. So I am also working with monoid actions, but quite often and in a different direction, like the model categorical setting. But I try to understand reversibility properties and then generate a model structure by using the covariant model structure. So maybe
really interesting.
Yeah, I think.
Yeah, so like there are. Yeah, so I often wonder about this question, and I don't really have anything good to say about it. But so particularly when you have this kind of stochastic stuff going on, you kind of inherently have this kind of information theoretic thing that says as you go forwards in time, you maybe, or as you go one direction in time, you maybe gain or lose information depending on the way you look at it. And that makes it kind of inherently directed. And that kind of it's not really, doesn't really come out very much in the structure. It's just kind of hiding there. But at the same time, I often think about the trajectories of these systems as being like paths, of course, in some space. And I want to know really the relationship between these paths in the kind of dynamical setting and maybe the kind of like higher categorical setting, something like this, and how, and whether there are like connections between these questions of information theoretic reversibility and stuff like directed like homotopy or like homotopy theory or homotopy type theory or something like that. But I don't know really. I haven't started thinking about that very much, but I feel like there should be connections, certainly.
Okay. I just wondered if, for example, if you wish to, if your system is not reversible, do you wish that reversible or in your setting? But
I don't. I
think, if I turn an irreversible system into a reversible one? Does it work for you? Like
that would be very. I mean, there are definitely. Yeah, I don't have a very good answer, but there are definitely cases in which answers to that would be relevant and useful to me. People often think about systems in these similar kinds of terms, but yeah, it's interesting. Yeah, very interesting.
Thank you.
Thank you very much for the question.
Thank you.
Thank you. Are there any other questions or comments? Well, if not, let's thank Toby again. Thank you very much, Toby.
Great.
Yep, I think we